This is 11-2D, Chemistry Grade 11, and our study of equilibria. The assessment criteria for this term, this activity, is to be able to predict the effects of a change of temperature, concentration, and pressure on equilibria. You need to understand why a catalyst does not affect the position of equilibria. You need to understand with examples why the reaction conditions for industrial processes involving equilibria are often a compromise, and you need to be able to predict the effects of changing temperature on the equilibrium constant and understand that the equilibrium constant is not affected by changes in concentration or the addition of a catalyst. We saw the effects on chemical kinetics, or the speed of a reaction, based upon changing temperature, pressure, concentration, surface area, and the addition of a catalyst. We will do the same thing when looking on the effects of equilibria on a reaction. Equilibria in a closed system is when the forward reaction is going at the same way as at the same speed as the reverse reaction. Now, the effects of equilibrium are listed below. We will try to give you an understanding in the lessons we provide of the reason why these changes are somewhat different than those that you will see in chemical kinetics. I found a rap video that might help you to remember what happens with the external factors, and I'd like to show that to you now.
SJ Mock Squad, we back at it.
Oh yeah! You rolling with the L now.
Jello Beats, holla at me.
Chemical equilibrium. Le Chatelier tell us how to shift on them. Reactants and products, different concentrations, always stay constant for reverse reactions. Reversible reactions moving back and forth. They always keep it happening, of course.
K equals equilibrium expression. Products on top, reactants on the bottom.
Use coefficients as their powers. Work for flower stamps like it's rush hour. Only include aqueous and gas. And if you don't know, get up at my chem class. I've been learning chem since like the 8th grade. If you're acting shady, you a lampshade. This a hard topic, we still get an A. Raise product concentration, listen when I say.
You already know that I shift left. If you decreasing, gotta shift right. Increasing pressure, I go all out. Favors less moles, know what it's about.
Decreasing though, favors more moles, no doubt. Exothermic, y'all know when the heat's out.
When reactions get heated, left is where it goes. Heat's moving right, temps dropping down low.
We gon' change the temp on the endo. Shifts right when you raise the temp though. Decrease in temp, make it go left on them. Also shifts for reactant concentration. Chem squad, that's what we are. X102, ain't that far. Increasing, shift it to the right. Decrease, shift left, that's right.
To find concentrations, use the icebox. Y'all know that chem rocks.
With my squad, I'm with Frank, I'm with James Mock. Ice initial change, equilibrium. Fill initial on the top row. Some change in the second though. Products and reactants make a ratio. Frank taught icebox about a week ago.
After that video, and after looking at the previous slide, you have noted that a catalyst does not affect the position of equilibrium. I hope you can see in this diagram the reason for that. We have already talked in chemical kinetics about a catalyst lowering the activation energy of a reaction. Now, the position of equilibrium, whether or not we have a catalyst, does not change. It just gets there faster. Many industrial processes take advantage of equilibrium effects. The formation of ammonia, called the Haber process, is one, as well as the contact process for making sulfuric acid is also one. In the Haber process, we have to balance temperature and pressure. In the formation of ammonia, the lower the temperature, the more likely we are to get products. But the lower the temperature, according to chemical kinetics, the more time it takes for that reaction to proceed. Also, if we look at the Haber process, if we increase the pressure, we can get more product. But making a reaction vessel that can hold up to, say, for example, 1,000 atmospheres is a very difficult process. So there is a balance made between temperature and pressure in order to make the Haber process work industrially. The contact process is similar. We want to balance pressure, temperature, and a catalyst so that we can get the most product in the least amount of time, and so that we can have the needed amount of pressure and the needed amount of temperature that could be available to us in an industrial situation. Again, we'll talk more about this in the classroom. Equilibrium constants are an indication of the concentrations of the products related to the concentration of the reactants. This table may be helpful in giving you an idea of how equilibrium constants change based upon temperature and based upon the speed of a reaction, whatever that reaction may be. End of year tests tend to like giving you equilibrium questions that do not involve computations of equilibrium constants, but talking about the trends as temperature and pressure change. You may want to look at this graph and place it in your notebook. This is a restatement talking specifically about temperature. And the factors that affect the position of equilibrium. Again, most of the end of year questions we have seen talk specifically about temperature and not pressure. Again, I would suggest that this or the slide before may be something for you to commit to your knowledge either through writing it in your notebook or looking at this podcast repeated times. After looking at those two flowcharts or tables, you should be able to identify that the addition of a catalyst increases both the forward and reverse reactions. So the equilibrium constant will remain the same because the numerator and denominator ratio will remain the same. A change in concentration will not change the equilibrium constant either. For example, if you increase the products, you decrease the reactions by generally the same amount. So again, that ratio, the equilibrium constant, does not change. Some questions to start your thinking. If a catalyst increases the rate of reaction, why does Kc remain the same? What are the ways to optimize an endothermic reaction to favor products? What are the ways to increase the equilibrium constant for an exothermic reaction? Remember to write down on a piece of paper the answers to these questions if you have not passed.